we're going to be finding the convection coefficient H, and H is in units of watts per square meter Kelvin, and this is opposed to finding the conduction coefficient K, which is in watts per meter Kelvin. So finding K is pretty easy. If you know the material you're working with, you can just go on the engineering toolbox, and it has a lot of data available, a lot of conduction coefficients for all kinds of materials, from dirt to aluminum to copper to brick, whatever you want, and you just look it up online. And then you can use K with, whatever your geometry to solve thermal problems. H is more involved, and it involves a couple different factors. The type of flow you're talking about, whether it's laminar, nice smooth flow, or turbulent flow with all kinds of eddies and vortices. It is dependent on the geometry, whether we're talking about flat plate or flow inside of a pipe, as well as a couple other geometries. It is also dependent on the qualities of the air or the fluid we're talking about. So how sticky it is and how well it diffuses heat. And so smart people, they did a bunch of experiments, and they came up with different empirical formulas for convection coefficient for various geometries. And these formulas that they came up with, they involve three different numbers: the Reynolds number, the Prandtl number, and the Nusselt number. So let's start by talking about the Reynolds number. The Reynolds number is defined as the ratio of inertial forces to viscous forces. So that inertia is defined as the tendency of a body to maintain its current state of motion, to resist change. So it is rho, which is in units of, that's the density kilograms per meter cubed. And this makes sense that this would contribute to the inertial forces of the fluid. If it's a denser fluid, it won't want to change. So think of it as throwing a bowling ball in the wind versus throwing a feather in a wind. A bowling ball is a lot denser. The wind isn't going to affect it, but it will affect the feather. V is in meters per second. This is the velocity term. And this also contributes to the inertial forces of the fluid. If it's going fast, it won't want to change as much. So if you shoot a bullet, the wind won't affect it as much as the wind could affect a paper airplane. And D, this is the characteristic dimension. And this is dependent on the geometry. If we're talking about fluid flow in a pipe, the characteristic dimension is going to be the diameter, and that's what we're going to use. If we're talking about fluid flow over a flat plate, it'll be the length of the plate. And the same thing with a wing. The characteristic dimension here is going to be the chord of the wing. And I do not know how this contributes to inertial forces. So if you do know, if you have any ideas, just leave a comment and let me know. And this unit is meters. This is divided by the viscosity, the dynamic viscosity, which is the stickiness of the fluid. This is in units of kilograms per meter second. Honey will have a very high viscosity, dynamic viscosity, and something like water will be lower and air will be even less than that. And if you look at the units here, you'll see they'll all cancel out. All three of these numbers are dimensionless. So this contributes to the viscous forces, the stickiness of the fluid. So next is the Prandtl number, is the next thing you'll need to find. And this is defined as the ratio of the tendency of the fluid to conduct momentum divided by the tendency of the fluid to conduct heat. So let's talk about the tendency of the fluid to conduct momentum. I couldn't think of any really good examples, so I'm just going to use a bath of honey with some kind of treadmill at the bottom of the bath. So we got honey up here. The whole thing is filled with honey. And you are able to move the bottom of the bathtub this way. We know from the no-slip condition that the fluid, the honey at the bottom, will stick and it will go at the exact same velocity as the treadmill. But how will the honey on the surface of the treadmill be affected? So the surface of the bathtub, how will that be affected? Well, it's going to move along with the treadmill. It'll move at almost pretty much the same velocity. It'll lose a little bit, not as long. The vector won't be as long, but it'll move because honey sticks together. It's a sticky fluid. Okay, so if you fill it up with water, how are these vectors going to look? Well, again, at the base, it's going to move at the same velocity as the treadmill, but it's going to lose velocity. It's not going to be able to diffuse its momentum as much. This vector should be shorter than that vector. And if it was just air, well, up here it's not going to be even affected at all. The air is just going to be still up here. It's, theoretically it will diffuse a little bit of momentum, but not a lot. So the numerator here is the tendency of the fluid to diffuse momentum. The denominator here is the tendency of the fluid to diffuse heat. This is thermal diffusivity, and this is the same alpha in the heat equation. It is defined as the ratio of thermal conductivity. It makes sense that if it is more conductive, it diffuses heat better, divided by the specific density times rho. So this would be these two units, specific, not density, specific heat. Joules per kilogram Kelvin, and times density would be kilograms per meter cubed. Kilograms would cancel out, you get joules per meter cubed Kelvin. So this would be the volumetric specific heat. And then, so conductivity divided by the ability of the fluid to store heat. This comes together to give the tendency of the fluid to diffuse its heat. So the tendency of the fluid to diffuse momentum, like in this bathtub example, honey's really good at this, and the tendency of the fluid to diffuse heat, which is a function of its thermal conductivity and its specific heat. So for air, you're going to have, usually the Prandtl number is around 0.7. For fluids, fluids are a lot better at diffusing momentum. So the numerator is going to be a lot bigger for fluids. So for fluids, you're going to be in the hundreds, or thousands. They're going to have a lot bigger Prandtl numbers. And these numbers you can look up. It's kind of like, you look up your fluid and you can find the Prandtl number. And for air, I think it's about 0.7. So once you have these two things, you can find the Nusselt number. And this is where the empirical formula comes in. Once you have the Reynolds number and the Prandtl number, you're going to see some kind of formula, and it's going to look a little bit like this. To the 1/2 and the Prandtl number to the 1/3. I'm just making this up, but it's going to be something like this. And that'll be your Nusselt number. So you plug in your values for Reynolds number, and you plug in your values for Prandtl number, and you get your Nusselt number, which is defined as the ratio of heat due to convection, convection divided by heat due to conduction, which are defined as the convection coefficient times area times gradient, and the denominator here, heat due to conduction, conduction coefficient, area, gradient divided by L. So there's a lot of cancellations here, and you are going to get the Nusselt number is equal to H times L, denominator. The denominator is the numerator, divided by K. So this this is the property of the air, and this is the property of your geometry. You solve for H, and this was the goal of this video, was to solve for H. So just as a recap, find the Reynolds number, figure out what geometry you're using, what characteristic geometry, find the Reynolds number, find the Prandtl number. This is specific to the fluid. In air, it's 0.7. Once you have these two, you go to the Nusselt number, the empirical formula. You plug in your values to find the Nusselt number, and once you have your Nusselt number, you find the convection coefficient. Once you have convection coefficient, you can use it along with your conduction coefficient and your geometry, and you can use it to start solving your fluid or your heat transfer problem. Thanks for watching.